Here we are with lesson 5 on exponential growth and decay. Let's start with exponential growth here. It can be modeled by the function y equals a times b to the x. Okay? And actually the decay model is going to be exactly the same. Here's what's different. This is the important part. A is going to be greater than 0, and b is going to be greater than 1. Not even equal to 1. It has to be bigger than 1. So 1.1, 1.01, 17, anything that's larger than the number 1. The base b we call the growth factor. Okay? So that's how much this thing's growing by all the time. It always equals 1 plus the rate of change expressed as a decimal. So some things we have to remember here. If we had something like 70%, to convert that to a decimal, we need to divide that by 100. So 70 divided by 100, in other words, we move the decimal 2 spots to the left, and we have something like 0.7. And so it's always, the growth factor is always 1 plus the rate of change. So 0.7 plus 1 is just going to simply equal 1.7. Okay, so you always have to take, if you have a percentage, you want to take it and convert it to a decimal and add 1 to that, and that's what's going to be your b value for your growth factor. Down here is the algebraic expression, how this thing shakes out here. So we have the initial amount, that's your a value. Okay, so whatever you start with. Okay, if you're talking about your money growing exponentially and you started with $100, that would be what your A is, the initial starting amount. Okay? The B, like we just discussed, is the base, and when it's greater than 1, we call this the growth factor. To find the growth factor, we always take 1 plus the rate of change. Okay, and x up here, that's our exponent. This is the variable, right? That's what's changing, right? X is, we call that our input, and y is our output. Okay, many times that x is going to be something like time, like years or months or days. It's not exclusive to time, but in many cases it's time. Think about your values on when you make a graph. The x-axis is always that time scale, and the y-axis was always something else. So in many cases, the x variable here is going to deal with time. And the graph of exponential growth always looks like this. It starts off very close to the x-axis, and it comes like a ramp, and it's a curve. There's no sharp edges to it at all. It's just a long curve, and it starts to go up faster and faster and faster and faster and faster. Okay, and so that's only when that b value is greater than 1. That's what we have, the graph of exponential growth. It looks like that. And this value where it crosses the y-axis is always this a value. All right, so it's pretty easy to determine exactly where it's going to cross the y-axis. All right, let's see how this works. Number of people who like something on social media often grows exponentially. So consider a post by a person that's then liked by 5 friends. Okay? Then, every hour, 5 of each of your friends like it also. So let's show how the total number of likes grow over time. Okay? You obviously are the first person to like it, right? You wrote it, so you must like it. So you're the first person. And then you have 5 friends who are going to like it, right? In 1 hour. So we have, 1, 2, 3, 4, 5, and then, let's do it like this. We have 1, 2, 3, 4, 5 people like it. All right, and then each one of these people has 5 of their friends who like it, right? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. All right, so let's break that up like that. All right, so first I had 5 people like it, and then I have 5, 10, 15, 20, 25 people like it. All right, well, each one of those 5 people have 5 more people who like it. So I don't know if I could break each one of these into 5. Let's see if I can do it. 1, so 2, 3, 4, 5, and they all have 5. And then this guy has 5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let me do that again. You can see how this is starting to get out of control. Okay, and finally, all right, let's count those up. Let's see. So I have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 105, 110, 115, 120, 125. 125 people. Of course, in the next hour, each one of these 5 people had 5 more likes, and I'm just absolutely not going to do that right now. So it'd be, like that, and each one of these has 5, and it's going to be a lot of people, okay? So you can see how this is growing very quickly, right? We started with 1 person who liked it, then 5 people, then 25, then 125, and so on and so forth. And this grows very, very fast. And that is the nature of anything that has exponential growth. It starts growing very, very, very quickly. All right? So after 1 hour, 5 people liked it, and after 2 hours, we had 5 times 5 people liked it, which is 25. Okay, and after 3 hours, we had 5 times 5 times 5 people like it, which was 125. After 4 hours, if we continued this pattern, it would be 5 times 5 times 5 times 5 people like it. And that's going to be 625 people. And after 5 hours, we're going to have 5 times 5 times 5 times 5 times 5 people like it, and that's going to be 3,125 people. So look at how quickly these numbers get really far up there. So in 5 hours we reached over 3,000 people with this social media thing. Okay, and after another hour this would go times 5 again, so it gets very, very big. But if you notice, what's going on here? I have 2 5s. Well, isn't that how many hours? And here I have 3 5s, and that's how many hours, and 4 5s, and that's how many hours, and 5 5s, that's how many hours. Okay, so let's try to look at our equation algebraically. Y equals AB to the x. Remember, A is the initial starting value. Well, how many people liked it at first? Well, just me, right? The one person sent it out. So A is going to be 1 here. So Y equals 1. Now, what's the growth factor? Okay, so how much is this growing by each time, right? And it's growing by 5 people, right? 5 more people like it every time, right? So the growth factor is this 5. All right, so the B value here is 1 times 5. Now I need to find the exponent out. So the exponent is going to be the amount of time that I need to be doing this for. So I want to find out how much it grows, say, over 6 hours. I would need to put the exponent here, the x, to be 6. So in 6 hours, I'd be able to figure out that it was 1 times 5 to the 6th power, or just 5 to the 6th power first I would have to do. And 5 to the 6th power is going to be this 3,125 times 5 again, which is going to be 25, 10, 12, 6, a very large number, 15,625. And that's how many likes this thing would have after 6 hours. Remember, that was my input, my x, and its time, and this is my output, how many people actually like this thing. All right, let's take a look at exponential decay. It's the same idea, except instead of growing very, very fast, it's going to get smaller very fast at first, and then it's going to continue to approach zero. It's going to continue to get very close to zero over time. Okay, so the initial part of exponential decay is going to be a very large amount of decay, and you'll see that amount of decay is going to decrease significantly every time. Okay, it can be modeled by the function y equals ab to the x. Still, same thing. A is still greater than 0. And this time our b value, it says 0 is less than b, but b is less than 1. In other words, b is right smack dab between 0 and 1. Okay? So any sort of decimal value will work here, like so 0.1 or 0.7 or 0.99999. Okay, anything that's less than 1 but greater than 0. The base b, we're going to call that the decay factor. And this time around it equals 1 minus the rate of change expressed as a decimal. So in other words, again, if I had 70%, okay, that rate is going to be 0.7. Again, I divide by 100 or move the decimal over 2 to the left. So 0.7, and now I have to do 1 minus 0.7, so the decay factor here is going to be 0.3. If I had something where the rate of change was 70%. Okay, so I need to become comfortable converting percents just in case they're thrown at us here. And we will talk more about it in the few lessons to come here. But let's look at this again. So again, the A is the initial amount. It's how much we start with. The B is the base, and it's the decay factor when it's between 0 and 1. Okay, so remember, when it's greater than 1, this thing's going to be growth. So when it's between 0 and 1, this thing's going to be decay. It's going to get smaller. And the exponent, once again, in many cases, that's going to be something dealing with time. Okay? The graph of exponential decay looks almost exactly like the exponential growth, just a mirror image across the y-axis. So instead of starting on the left and getting larger, it's going to start very large and get very, very small and get all the way to where, see, if you notice, it's not actually touching the x-axis. It just kind of keeps getting closer and closer and closer and closer to the x-axis, but never really does touch it. Let's see how this models. Okay, so if a family buys a car for $20,000 and the value of the car decreases by 20% every year, after 6 years, the family decides to sell the car. So, should they sell it for $4,000? And we want to explain that. So let's see. So initially, the car was worth, after no time has passed, they bought it for $20,000. Well, after 1 year has passed, the car has depreciated by 20%, right? The value of this car has gone down by 20%. So how can I figure that out? Well, I take the number 20,000, the starting point, and I can either do it like this. I could say 20,000 times, again, 20% as a decimal is going to be 0.2. And if I do that, I will get 4,000. But that's not how much the car is worth, okay? That's how much it went down. So I need to actually subtract that from the initial point. So 20,000 minus 4,000 is 16,000, excuse me. Okay, so that's one way to try and do that. The other way to do it is if it's going to decrease by 20%, how much do I have left of the starting value? So if it decreased by 20%, I would have 80% left. And if that's the case, and that's actually the number I'm looking for, is how much I have left, then I can just multiply by whatever 80% is as a fraction. I'm sorry, as a decimal. So again, move that over 2 spots by dividing by 100, and I have 0.8. So let's try it. We'll try it again from the 20,000. So 20,000 times 0.8. And in your calculator, if you do that, you'll see that equals, again, 16,000. Okay, so if I have 16,000 and I have 80% of that left after year 2. Well, now the car is only worth this much. Let's see how much it's worth after year 2. So I would again multiply this number times the 0.08, or 0.8, I'm sorry. And 0.8, that's going to equal 12,800 using my calculator. So to find out how much it's worth after year 3, well, I would start with 12,800 and find out what 80% of that is. So once again, I start with 12,800 and I multiply it by 0.8. And this time I get 10,240. If I were to continue this process, I would see that after year 4 I have 8,192. That's how much it's worth. And after year 5 it'd be $6,553.60. And after year 6 it will be worth $5,242.88. Okay, but there's a much easier way to do this. Instead of having to do this 6 times, or say I wanted to know how much the car was worth after 15 years, I certainly don't want to have to do this 15 times. Okay, so let's think how this works. The initial starting value is always year 0, okay? It's how much the car was worth when we first got it. So let's try to figure this out. So A is going to be 20,000. That's how much the car was worth, the starting value. Okay, B is the decay factor, right? And it's 1 minus the rate of change. Well, if the rate of change is 20%, we already agreed that's 0.2. Well, 1 minus 0.2, well, that's that 0.8 that we were just using a second ago. Okay, so this B value is going to be 0.8. And if we want to find out after 6 years, remember, many times this X value is going to be the amount of years. So how many times are we going to depreciate this by 80%? We're going to do it by 6 years. Okay, so all you do is you take this, you put it in your calculator. So you say 20,000, use parentheses, then use parentheses again, 0.8, and then you raise it to the 6th power, and you will get $5,242.88. All right, so picking out what this was your A, and this was your B, okay, and this was your X up here. That's that Y equals A times B to the X. And this is how much the car is now worth after 6 years. So the question said, the family decides to sell the car after 6 years. Should they sell it for $4,000? I don't think so, right? They're going to be losing a bunch of money if they sell it for $4,000. They should probably try to sell it for at least, maybe $5,300 or $5,500, and then they can make a little bit of money on the car. All right, so that's how exponential growth and exponential decay work. We will be working with it more in class, obviously, tomorrow, and or next time we meet. And that's it. So just try to keep track of the big thing here is to remember what the B is. If B is greater than 1, it's growth, and if B is between 0 and 1, it's decay. All right, I will see you all next class.